Hello, welcome back to CMSC398L. And this is the third week for our class. And then this week, we'll be talking about enumeration and basic searching, which is actually a very important thing to solving problems. It's not a very hard thing, but it's very important when it comes to solving problems. So, imagine one day you and your friend are discussing about a problem and then they just tell you that, oh, for this problem, just do brute force and then search for the answer. Yeah, and that's it. That's so easy, right? But you just don't know what they mean, and then you just think about what do they mean by brute force? How do I even brute force for this problem, or how do I search for this problem? Yeah. So this is what we'll basically be talking about today. So for today's content, we'll talk about these seven things, and then I will briefly talk about how these technique works. And then in class, we will be talking about other problems that we can apply these techniques. So let's get into the first one, which is pretty simple. Yeah. So now you want to search on an array, and then for this example problem, I'm going to be talking about this problem, which is the maximum subarray sum, which, if you have taken 351, you might know the ON solution to this problem. But now, we want to know how to search on this array. So the problem tells you that you are given an array of size n, and you want to find the maximum sum of elements over all the subarrays. So for a subarray, it's just you can take some LR and then find the elements from AL plus one to AR, and this will be a subarray of A. And you want to find the maximum sum of elements over all the possible subarrays. For example, -1 is a subarray, and then maybe -2, -5, 3, -2, 5, 3 is also a subarray, or like that. And now you want to find a subarray that has the maximum sum. Yeah. So the maximum subarray would just be 3, -2, 5, 3 in this case, and the sum will be 9. So how do we know, how can we find the maximum sum? So the basic idea is that the naive idea is just that we can use ON cube solution. So the idea is that since we want to find the maximum sub over all the subarrays, why don't we just find a subarray L to R and then check for all the L and R? And after a subarray, after getting that subarray, we can basically just sum the elements up in ON and then take the maximum, right? So the first step, going over all the L and R, takes ON squared. And the second for loops, which is the for loop that goes through the subarray, takes ON. Therefore, it is ON cubed, which is actually pretty slow, right? Like usually this problem will give you maybe n is less than or equal to 10 to the 6. And if you apply the thing we talk about, which is 10 to the 8th number of operations, as approximately 1 second, and this will run too long. So we wouldn't really want this kind of approach. So think about this. Do we really need to go through the subarray every time we are doing this? And you'll see that, yeah, we are actually doing the same thing over and over again because if we just want to find a sum, we can actually just change it like that. We can just put a sum here, and then while we are increasing this r, we can fix the left bound and then move the right bound. Then each time, what we are doing is that we can just accumulate this sum and then just take the maximum of that. So this kind of way reduce O(n) cubed into O(n) squared. And usually for many subarray problems, this will just be how you search for the array, how you search for the subarrays. Yeah, but that is actually still not a good enough algorithm. So if we get to gradient DP, we would definitely talk about the next solution, which is um, Cadence algorithm. And then yeah, so you might also have learned it before. So you can try to think about it as a greedy algorithm with DP, algorithm, but like we'll not talk about it here because like we will talk about it maybe for the next few weeks. And we can further optimize this algorithm into ON algorithm. And then basically you just keep track of the max sum and then the current sum, and then just do something similar to like doing a DP. And then we will skip the details here. And then if you are interested, you can just go learn. And then if you have taken 351, you must like already know about this. Okay, so this is basically how you search on an array. But like actually, if I want to be precise, it's like searching over all the subarrays. Yeah, so basically you can just use a for loop to enumerate through all the subarrays. But what if now we are searching for something else and it's not subarrays? So let's look at a very classic problem called the traveling salesman's problem. So basically, this problem tells you that there are n cities in some country numbered from 1 to n, and then you are given the distance of all pairs of cities, and there is a traveling salesman at city 1. And now, today, the traveling salesmen want to find the shortest possible route to visit all the city exactly once, and they want to return back to 1. Can you find the minimum route for the traveling salesman? So like basically you'll be given like this is actually similar to a graph problem, but like we will not really talk about it graph now, but like you just you can actually like don't think about it as a graph, but like just as a maybe you're given a map and then you know the distance between them. And then maybe it's like 2, 3, 4, 1, 5, something like that. And then the shortest path that they can go through and then go back to and in return it's actually just like maybe you just take this route. Like you go from this one to this one to this one, this one to this one, this one to this one. And it will probably give you the shortest one. Yeah, I think that's correct. So basically you just want to start from some vertex and then go through all the cities and then go back. That is basically what this problem is talking about. And then you have to visit all the city exactly once and return back to 1. So this problem is very classic because it's actually a NP complete problem if you know what that is. And then it's actually not easy to like find this optimal solution for this one. But the thing is that now n is very small. So like we can actually search for all the routes that visits all the cities exactly once. So suppose there are now 4 cities, then the possible routes are so you just fix the starting point to be 1 and the ending point to be 1. And then the middle points, you can just permute them. So like you can just permute like 2, 3, 4, 2, 4, 3, 3, 2, 4, 3, 4, 2, something like that. And then you can see that they are actually just going over all the possible like 3 factorial of the number of permutations, right? So last week we talked about that in C++ standard library, there's a method called next permutation, and you can just use that, and this will take on factorial. So pretty much what you want to do is that like we will sum up the distance after going through a permutation, and this will take O of n. So this approach will take you on times n factorial. And then if we get to dp, we will learn how to solve this problem if n is now 20. But yeah, it is a slightly improvement. And then because like it's a NP complete problem, so like usually in competitive programming, it just like takes like exponential time. Yeah. Okay. So after talking about like this problem tells you how we can search over all the possible permutations. And the next problem will be searching over all the possible subsets. So here we are also going to talk about a very classic problem called the knapsack problem, which some people might know from doing DP problems. But like here, the constraint is unbounded, which means that like the weight is not bounded and then the capacity is not bounded. and now there are 20 items. How can we do this? So for this problem, if you need to think about it, you can stop and think about it. But like this problem, the basic idea is just that for each of the item, you can either pick it or not pick it. So this leads us to a solution that like we actually can just use a recursion and then keep track of the current sum and keep track of the current like sum of values and sum of weight. And then when the weight is greater than capacity, you just return. Otherwise, you just go through all the possible possibilities, which like you take the item I or not take the item I. And then that's basically it. So this solution takes O2 to the n. And yeah, it is a pretty classic recursion example. But in competitive programming, actually, competitive programmers hate recursion. And there's a reason. It's because that like if you actually run the code of a recursion code and a iterative code, then you will see that the code that you use recursion is usually much slower than using a iterative method. So we actually have another way to do the same thing, but like you just use a for loop and do everything. So the second way is what we call bit mask iteration or something like that. So what we will do is that for each item, you either take it or not take it, right? So we can actually represent each of the states as zero or ones, like with zero or ones. So it's equivalent to like being an integer, right? So like the state for those three items will be like maybe you don't take anything, it'll be 0, 0, 0. If you take a certain one, it'll be a 0, 0, 1. And then if you list everything down, you will see something special. Like if you actually think about bit math, bit strings, or maybe just think about like yeah, just something like that. And you can see that these numbers are actually 0 to 7, which is 0 to 2 to the 3 minus 1, right? So we can abuse this kind of idea and then write a for loop using this thing. And then uh, just in case you don't know what a bitwise operator is in programming languages, this symbol AND is called AND. This symbol is called OR. This symbol is called XOR. This symbol is called left shift. And this symbol is called right shift. And I will not talk about it in this video, but like you can just look it up because it might be faster than I'm explaining it to you. Yeah. So then what we can do is that like we start from mass equal to 0 and then go through to 2 to the n minus 1. And then each time we check like if this for each of the bits if we actually take this item or not. And then we just go through all the possibility and see that if the sum of weight is less than or equal to this capacity. If it is, then we just take it. Otherwise, we don't take it. That's basically this problem. Yeah. So this way, it's actually like if you just consider the complexity, it's slower. But usually this way will actually run faster than the previous one. And actually, yeah, it's just like not much different. So yeah, you can try to use this. And the reason that this is not much different is because like n is usually just less than 20. So 20 is usually just like a constant. So like it doesn't really matter that much. Yeah. Okay. So the next thing we'll talk about is complete search. Actually, for the previous like examples, they're all called complete search. So what complete search means is just that like we go through all the possible possibilities and then we find the answer and take the maximum minimum or something like that. So the next thing we'll talk about is like how we use recursion to like write complete search. And that is probably one of the easiest and the hardest thing to do. Like if you actually like when you learn about maybe your first programming language and when you learn about recursion, maybe you'll be taught to like do something similar to this because like it's a very good example and very good like practice for you. And usually this kind of problem will require a lot of code and it's usually annoying. But like they usually don't require too much knowledge. So if you just not too good at solving like math problems or something like that, usually this kind of problem will be pretty good for you to like get points in contests. Yeah. So let's look at a classic example that we will use complete search. So the example that we're going to talk about is Sudoku. So this thing is the game that I think everyone knows. Like you're just given a 9 times 9 board, and then you want to fill in the board with 1 to 9, such that like every um, row and every column does not contain duplicate numbers, and also for each of these 3 times 3 boards, there also cannot be duplicate numbers, and that's basically Sudoku. And then now you're given a board pre-filled with numbers, and you want to find a single solution to Sudoku with the starting board, that is this board. Yeah. So how can we do this, right? So this problem is just very classic. Like we can just task, like we can just start from maybe 1 to 99, and then we just task out a number. Maybe here we put a 1 here, and then we see that, oh, it doesn't really like conflict with other numbers. And we first put the 1 here and then go 2. So 2 doesn't conflict. And then we go to next one, go to next one. And then maybe we feel like it was other numbers. And then we just try all the possible numbers. And if we don't, we just backtrack, which is just like, you don't really need to think about it, but like, it's just like when you do recursion and it fails, it will just go back to the previous state. But like you don't really need to think too much about how it works. But like it's just like a kind of thing that we would say. Like we would call this a backtracking problem, but like it's basically just do recursion. And each time when you place a number, you will need to check whether this board is valid or not. And if it's not, you just have to return or maybe just stop here, return from the function or stop doing anything you are doing. And then you will see that like by checking whether the board is valid or not, it's called pruning. Or else, if you just check all the possible like 90 to 81 possible boards, then this thing is just too big. Like I don't even know. Like it's probably very similar to like maybe 10 to the 60s or something, and then it is too big, and then it won't pass. So like we would need to use some way that's like better, which is like cutting off the unvalid board, and it will actually just pass. Yeah, and then you will probably want to try to write it on your own because like this is a very good practice for you. But like we will probably not make it required homework because it's very annoying. But like it's actually a good practice problem for coding. So yeah, I would recommend you to like at least try writing like some of these problems on your own. Yeah. And then in class, we'll also talk about another very classic problem that's like backtracking, which is the 8 queens. And we will leave it to Spencer and Madden to talk about those. Okay, so the next technique I'm going to talk about is 2 pointers. And the problem I'm going to talk about is this problem. So this problem tells you that you are given an array of length n, and you want to find the number of subarrays such that it has at most k distinct values. So to do this, you now see that we want to find the number of subarrays. So as what we thought, maybe what you want to do is just that we will search on the subarrays as what we just talked about. So this will take O(n) squared to like go through all the interval, but like you also need to maintain the number of elements with some kind of data structure. So this can actually just be done with map because like what we want to do is like we want to keep track of how many distinct values are there. So yeah, and this can basically be done with map. And you can make it O n squared or maybe O n squared log n. And it depends on whether you're using ordered map or ordered map. Yeah. But there is actually a better way. So for example, if we have an array, like maybe we have 5, 4, 2, 4, 5, 1, 2, something like that. Then here, because we know that we want a subarray that has at most k distinct values, so that's set maybe k to be equal to maybe 2, right? Then yeah, so that's set to be 2. Then the thing is that like we can keep track of a pointer here called L, and we can keep track of another pointer here called R. And then you see that if we expand R, we can actually like include the subarray because the subarray only has one distinct values. And then we can extend it to be this. This subarray only has two distinct values, so it's also valid. But if you increase R to the right, then it will not be a valid subarray. So we stop here. And we see that when L is 1, then there are two subarrays, which is just like R minus L, which is 2 minus L is just 2 minus L plus 1 is just like 2. So like you add 2 to your answer. And then now we'll move L to the right. And then we'll expand R. And then if you expand R, R will be expanded here. And then these will still be a valid subarray. And then you can do this. So basically, what we will do is just that like we will define the subarray with at most k distinct value to be good. And then every time you will try to move R to the farthest index, and it can be moved so that like LR is still good. And you will add R minus L plus 1 to the answer, and then increment L. And we also use setter map to keep track of whether the subarray is good. And if you don't know what I'm actually talking about, I will recommend you to like stop and trying to write it down yourself. And then basically you can look at this code and the implementation is just like that. And then there are actually a lot of ways to like implement the same thing. But like this is the way I usually will do when I implement this kind of thing. And then this is actually a very important technique. So I'll just leave you to like read the code on your own. And if you know what it is doing, then you can just go into the next part. If you don't, then in class we also talk about some other examples to try to let you know more about like two pointers. And also like besides counting the number of subarrays, we can also use to find the longest subarray that satisfies some condition. And we will show this by some examples in class. And yeah, Spencer and Mazin will talk about it. Okay, now let's just get into the last technique we'll talk about, called the sliding window technique. And this technique is just very similar to two pointers. And actually last week we also talked about something similar in class. So let's look at an example. Yeah, so basically this problem is just telling you that like you are given an array of length n and some integer k, and now you want to find the maximum elements in all the subarrays with size k. So it might kind of be hard to like understand what the problem is saying, but like basically what I want to say is just that maybe you have an array. I will just use this one, and maybe k equals to 3 here. Then we'll go to all the subarrays like this one. Then the maximum will be 5. And then now we'll go to the next subarray. The maximum will be 4. I will go to the next subarray. The maximum will be 5. We'll go to the next subarray, and the maximum will be 5. And if we go to the next subarray, the maximum will be 5. So the answer will be 5, 4, 5, 5, 5 if you have this array and then k equal to 3. So that's basically what it means. So actually, this problem is like you want to find a way to simulate doing this thing on this subarray. So when we want to do this, we also want to like keep track of the maximum elements. So to keep track of the maximum elements, we also will want some data structure that could help us insert, erase, or get max all in O log n. And I believe now everyone knows like what data structure can do this. It's the set, or maybe multi-set because we might have duplicate numbers. Yeah. And now we also need some kind of way to simulate the windows line to the right. And we can simply just look at an example code to like know how to do this. You see that like we have a multi-set to keep track of the numbers in the current window. And each time we'll just insert the new number to the window and then remove the so like what we'll do is just like if we have a window here, if we have a window here and we want to move it to the right, right? Then we will actually first erase the first element. We'll first erase this element, and then move this to the right. And we will insert this element, erase the front, and then insert the last element. So this is what we are basically doing in this code. We will move it to the right and then um, insert this element. And then when we move to the right, we'll erase the beginning and then output the maximum. We'll also output the maximum elements. And that's basically it. And I would recommend like you just try to think about it or maybe try to code it on your own. And this is basically what I'm going to talk about today. And yeah, and we will see you in class for talking about more and discuss about more of the problems. Thank you.